Thank you, Brett, and hello, everybody. So great venue, right? And good keynote to start the morning. So happy you're all here with us. So like I said, my name is Pete Johnson. I'm the Field CTO of AI, and welcome to 5 core embeddings choices for developers. See my clicker. For Christmas of 1981, I asked for an Intellivision. For those of you that know your old school home video game systems, you know that that was attempting to challenge the Atari 2600 for home supremacy. And you, sir, in the back, I can see from your laughter and your head shaking that you know exactly what I'm talking about. So this is what I asked my parents for Christmas Christmas of '81. What I received was the TRS-80 color computer seen here in the right-hand part of this picture. This picture was taken on my 12th birthday in February of 1982. That thing had 4K of memory. If you look to the side, it had an audio cassette player for storage. So I am not quite punch card old, but I am audio cassette player as storage old. So I tell you this not only so that we can get to know each other a little bit, but also so that if I make a bold statement, you might actually believe me. So my bold statement here, that is the premise of my talk here today, is that vector search is the new frontier. The key to making good AI applications is to be good at vector search. And I would also submit to you, it's also a big part about having a stable career going forward is understanding how to do this and how to do it well. So how do you do that? Well, the title of this talk is the 5 core decisions, and here they are. And here they are. Did you get it down? Did everybody write that down real quick? It was those 5. So what we're going to do, if I go back one, so the 5 decisions that you have to make when you create an embedding, it's chunking, similarity, numbered dimensions, quantization, re-ranking. I'm going to go into each of these in depth, but the way we're going to spend our time together here, I'm going to tell you how we got here. Why did vector search become so important? What are the circumstances in the industry that caused this to be a skill worth attaining and a functionality worth having in your AI applications? Then I'm going to walk through each of the 5 decisions, and I'm going to hopefully convince you that MongoDB makes it easier to make each of those decisions and to make them well. Then at the end, I'll give you a little bit of review. I'll give you some next steps. I don't expect you to take my word for all the things I'm going to say. I'll throw up some QR codes. You can take your phone. You can get some links to some training that our friends at MongoDB University and actually Apurva, who did the demo here during the keynote, that she constructed so that you can get your hands on. Don't believe me. Go use it yourself. So how did we get here? So if you go back to 2022, 23, the way that you would interact with an LLM is you take your query, you put it in the context window, the LLM would process it, and you get back some response. And this was awesome. The only thing that wasn't awesome is that an LLM has a knowledge cutoff. So there is a point in time at which the data that it's trained on doesn't go past. So what if you need an answer beyond that? Or more to the point, what if you have some proprietary data that you need the LLM to interact about? Sometimes you need the LLM to forget that it knows who the last 30 Oscar winners were, and it knows something about your business with some proprietary data. If you were to retrain the LLM, this is an expensive proposition. Even if you were to retune the LLM, that is also an expensive proposition. There's got to be a better way to get your proprietary data into an LLM as part of this processing. And that's when in 2024, people started talking about retrieval augmented generation. Instead of taking the query and popping it straight into the context window, instead, you would have a data ingestion phase, where you take some unstructured data at the bottom in the middle of the screen, you pass it through an embedding model, like, I don't know, a Voyage AI model, and you put it into a vectorized database, something like MongoDB. Then, at query time, you would first take your prompt and do a query of it against that vector database, take the documents that get retrieved as part of that, take that with the original query, put it in the context window. Now you get a very focused LLM that forgets who the last 30 Oscar winners were, can help answer questions about the proprietary problem that you're trying to solve. So this was 2024. Last year in 2025, we started to get a more sophisticated version of this with agentic interaction, with things like tools and session memory. Session memory, in addition to RAG, is also a great use case for vector search. My friend Makiko at 210 and the other venue is doing a talk just on session memory. So if that's an interest of yours, Apurva talked about that a little bit during the keynote. You can get more information during that session memory. But what we're going to do is we're going to zoom in here. Because vector search is the new frontier, we're going to zoom in on what it's like to do this for RAG. So Frank mentioned this during the keynote. There's use cases where lexical search or keyword search just kind of doesn't cut it. And the reason for that is if you really examine what lexical or text search is, first of all, it's text only. So some of that multimedia stuff that we saw during the keynote isn't relevant to just text search. And it turns out the corpus of your data has to closely match the way that your users are searching it. You can get away with some things with some synonyms and so forth, but some of the examples that Frank and Apurva showed you this morning showed that even for text, let alone multimedia like image, audio, or video, you need some way of bridging that vocabulary gap, and semantic search or vector search is a great way to do that. So how do you know if you have a good vector search? What does vector search a good one even look like? And what I would submit to you here today is that MongoDB vector search is better when judged by 3 criteria that we're going to talk about as we talk about those 5 choices. Number 1, higher retrieval quality. That should seem obvious that the better retrievals that I get out of my query, the better my overall AI experience is going to be. Oftentimes, as we're going to see here in a minute, there's this trade-off, this balancing that you have to make between retrieval quality and storage cost. Sometimes you have to iterate over different permutations of storage cost and retrieval quality. There's going to be one example I'll show you here in a minute where you don't have to choose. And then how easy or difficult is it to use the system? One of the ways that I talk to people about this is more people will build AI applications in the next 3 years than have built AI applications in the past 3 years. How do we achieve that as an industry? By making vector search easier. So for each of the choices, I'm going to highlight retrieval quality, storage costs, and what the friction is for the developer trying to lower their learning curve so you can understand how to do it better. And that starts with, because we have the document model, if you want to add embeddings to an existing structure, all you have to do is add an attribute to your existing document. As you might know, the document model that we have in MongoDB, not every document in a collection even has to have the same shape. So if you wanted to, you wouldn't have to add this to every single document, just the ones that you want to try to implement vector store on top of. So that's how we got here. This is why vector search became important. So let's now, one at a time, go through our 5 core embedding choices. We're going to start with similarity. I'm going to start with similarity because if you're not familiar with how vector search works, similarity gives me some structure with which to talk about it. So what does vector search really mean? You're taking some concept. In this case, we're gonna do a search on just simple words. And it allows us to take, in this case, English words and turn them into a numeric value, into a multi-dimensional representation of a particular piece of information. So all we have here, everybody in here probably took algebra at some point. You've seen an XY axis like we have here on the left-hand side. And we have a corpus of data that's just 4 simple words: dog, cat, apple, orange. You would imagine that dog and cat would spatially be closer to each other in this space because those 2 words have more in common than, say, apple and orange, because dogs and cats are not only mammals, they're mammals that people have in their homes, whereas fruits and vegetables are a completely different kind of thing. So what the embedding models do is they help capture the semantic meaning of that data and map it in a space. This is 2D space, a simple 2D space so that we as human beings can understand it, unless you're somebody like Tenyu Ma, who's our chief data scientist. That guy can think in 1024 space. I cannot. So we make this as a simple example for what this looks like in 2D space. So now that we've got our corpus of data, suppose I need to do a query for kitten. If I try to do this with keyword retrieval, those 2 words are different enough. Kitten isn't exactly a synonym for cat. But we know as English speakers that those 2 things are related. Notice how spatially it's closer to cat than it is to dog, or certainly apple and orange. So, but how do you actually measure that? How do you measure the closeness? This is where similarity scores come in. The 3 most common is you might use Euclidean, which actually measures the distance shown in this example in 2D, but it could be 1024 dimensions. How close are those 2 points in space. You can use dot product, which maps one vector on top of the other, or what we recommend most people start with is cosine. It's a little computationally simpler, but it's still pretty accurate. It measures the angle between any two vectors. The wider the angle, the less alike they are. The tighter the angle, the more alike they are. How do you do this in MongoDB? How do you set the similarity function? It's pretty simple. When at indexing time, you tell us which function you want to use. You don't have to do any math yourself. You just tell us which one you want to use, and that's how we reduce the friction for you to learn how to do this in vector search. So that's similarity. Now let's do chunking. This one's actually my favorite one. The problem with chunking, so how big are the pieces that you're going to put through your embedding model? The example we just did was individual words. It's a little more common to do a sentence. But the problem with chunking is that if you make the chunks too small, you lose the context of the broader information that that sentence might exist in. We've all seen sentences that might exist in two different documents. What differs them in those two different documents? It's the rest of the paragraph, it's the rest of the page that gives that context. So if my chunks are too small, I lose that context. If my chunks are too big, the details start to get lost, and I have to start to increase my storage costs. So this is one of these examples I talked about before, where you might need to make a trade-off between retrieval quality and storage costs. If only there was a way that I didn't have to choose. What if I could get better retrieval scores with a lower storage footprint? If I could do it with smaller chunks. And if I didn't even have to think about it, that would be easiest at all. That would hit all three of our criteria we talked about. Well, this past summer, the Voyage team released a new kind of model that had not yet been seen in the market for text embedding. It contains a feature called contextualized chunking. The idea here is you pass us the chunks and you pass us the documents separately. It's part of the same API call, but you pass them separately. We will take the context from the document and we will embed it in the same chunk with your smaller chunk size. You see here on the right-hand side, the blue line there is the traditional, at the time, Voyage 3 large, and you see the retrieval quality on the y-axis increases as the chunk size gets larger along the x-axis. But with the context, with the contextualized chunking, we can flip that. That you can actually get better retrieval scores with smaller chunk size. So now I don't have to think about the chunk size anymore. I don't have to go through iterations. That helps my friction. I can get better retrieval scores with smaller storage footprint. So that makes it the perfect feature for our criteria for what a better vector search is. That's chunking. What about number of dimensions? What we looked at before was 2D, because like I said, I can think in 2 dimensions, so can anybody who's done algebra. The number of dimensions is really the number of elements that are in that array of floating point numbers. If you've got more dimensions, that gives you more space with which to get accuracy and better retrieval quality. But it also comes at the cost of larger storage size. So what commonly developers have to do is they have to choose one number of dimensions, see what the retrieval quality and storage cost is, and then try it again, iterate over it a second time. But this is costly, because typically with a traditional model, embedding model, you have to re-embed your entire corpus of data every time you want to try a different number of dimensions. If only there was a way to do this in such a way that I could embed my content once and then try smaller numbers of dimensions to see if I can get the right balance between retrieval quality and storage. For about a year now, every single Voyage model has used a methodology called Matryoshka representation learning. And what that is when the individual elements of the vector are created, they're ordered. So for example, if I wanted to try 1024 and I see what my retrieval quality is, to go from 1024 to 512 with a traditional model, I got to rerun my whole data through that. With an MRL model, I just chop off the last 512. They're ordered. So that doesn't solve the problem of retrieval quality versus storage cost, but it helps you get to that answer faster with less friction. Let's talk about quantization. So quantization here is, how am I going to store this? Typically, an embedding model will generate content at a full 32-bit floating point, but what if I want to give up some retrieval quality to store that at a lower fidelity? I could go full fidelity and get 100% performance. And this example here is if you had a chunk size of 3 megabytes. I could use scalar quantization, so that'll take that floating point number and instead scale it back to an 8-bit integer. I take a little bit of a hit on my performance, but I get a little bit of a saving on my storage. With binary, I get a bigger hit on my retrieval quality, but I get a bigger savings on my index. So how do I play with this inside of MongoDB? Just like we saw with Similarity score, all you got to do is when you set up the index, you change what the level of quantization is. You don't have to do any math, we'll do it for you. Now you can do it at the model, the core model itself. You can do it as you generate the corpus of the embeddings for the corpus of data, but you can also do it inside the index. Again, trying to make the friction, trying to make it so that you can try your iterations to get the right balance of retrieval quality and storage costs for whatever your particular use case might be. So we covered chunking, we covered similarity score, we covered number of dimensions, we covered quantization. The last one we're going to talk about is re-rankers. Most people don't really even know what that is or why you might need them. It turns out that when you go through and you do a query in a vector database, you get the retrieved documents, they're not always in the most logical order. I think we've all had the experience of when you interact directly with an LLM, whether it's a chatbot or you're doing it through the API, the order in which you give it content sometimes impacts what the retrieval is that you get back. And it turns out that if you use a re-ranker to reorder your documents in a more logical way, you can get a boost to your retrieval score. So it doesn't cost you anything in terms of retrieval quality. It doesn't cost you anything in terms of storage costs. If you choose to do this, you get a little bit of latency because you're running this through a second model before you send everything to the LLM. But depending upon your use case, that boost in relevance might make a big difference. It could be the difference between a valid answer and a hallucination. So that's our 5 core choices that we can make as we're trying to create the best vector store. I have 2 minutes left. I would urge you at this point to take out your phones if you're interested in learning some more about this. I laid out what these 5 choices are, why MongoDB and Voyage makes it better. In 2 slides, I'm going to show you some QR codes that you can use to go get your hands on it yourself. Don't believe what I just told you. Go try to play with it yourself and find out. So we went through these 5 choices. You tend to think of it as, I'm just going to take my data, I'm going to run it through an embedding model, and generate my vectors. But these 5 choices that you make can make a big impact on whether or not you're successful with that vector search. So we got chunking, similarity, number of dimensions, quantization, and the re-rankers. Hopefully, you agree with my premise at this point that vector search is the new frontier. Hopefully, I've given you some guidance on what it is to make a good vector search and how you can personally get better at it. If you don't have that phone out already, I would urge you to do it now. That friction, that applies even to how we teach how you do this. So if you are the kind of person that likes short form learning, I just want to know the basics, I've only got an hour, I want to play around with it. Our friends at MongoDB University have the MongoDB skill program, that QR code on the far left, that's the one for you. If you like a little longer form, but you still like it to be directed, I want to get my hands on this, but I want somebody holding my hand through it. The middle one here, our friends at MongoDB University, it's a little bit longer form. It's building Gen AI apps. And if you're the kind of person like I am, I just want to go and fail and stumble, and that's how I learn. Our friend Apurva, who did the demo during the keynote today, she's got some content in a GitHub repo where it's free form, undirected. All of these are free. Generous free tier for both the base Atlas product and for the Voyage AI models. With any of these, I would encourage you to keep these 5 choices in mind and go play around with these yourself. If you enjoyed what I had to say here today while we were talking, I dropped on LinkedIn a comic book version of the talk that you just saw that I used Gemini to create. In addition to talking about MongoDB, I look at all kinds of things going on in the industry, whether it's different deals or different presentations. My DMs are open. I'll literally talk to any of you. Thank you for your time. You have a choice of how you spend your time, not only coming to the venue today, but also while you're here, and I appreciate you chose it to spend it with me. Have a good rest of your day.